So, oh, is this all we got? Anybody want more candy? You can have candy. You get the look in your eye. Yeah.
I get sick.
Yeah, at least you had 4 already. Okay. Jeez. Well, why stop at 5? So, I was telling some people before it came in, I actually am feeling a little under the weather. I know I don't have COVID because I took a rapid test and it's negative. I'm still feeling the effects from the vaccine, believe it or not. So it's not bad. I was just lifting weights today and I had to stop. I was feeling too fatigued. I'm doing a lot better than I did on Friday. Well, part of the thing was I stopped lifting weights when I was like in the heat in like the unvaccinated part of the pandemic. So I don't know how it compares last time, but I'm actually the booster shot was easier than the second shot.
How was it good?
From my second shot.
Your booster?
Thursday at 5.
So 2 quarters.
Yeah. So yeah. And I was getting a couple emails and people asking questions about if they should get the booster. And I do want to remind you guys, I'm not a medical doctor. And like, I mean, as you know, I'm very, very pro-vaccination, but I also want to let you guys know, I mean, people have individualized medicines and like, conditions, and it's something I don't want to say a blanket statement because, I don't know the risk versus rewards for you. And I don't want to use my authority as a teacher and say, no, you should totally get this. And then it turns out to be the bad medical call for you. So I don't really want to tell anybody to do it. For me, myself, since I mean, partially my age. I mean, I'm 42 and you guys are late teens, early 20s. So, and since I'm older, a lot of the risks are just not there for the vaccination. And also, although I had Moderna and I'm still at 70-ish% effective, even now, I wanted to boost it up to almost 100%, to 95 plus. So, but anyways, yeah. I'm tired of that C immunity. My immunity is actually quite good, as evidenced by the fact I still feel like crap. So it shows you my immune system's working pretty well, which is good news. I'm happy. I'm really happy that I'm feeling like heck, so I'm trying to, keep my speech to, PG levels, of course. So insert whatever words you want to say. But yeah, I just wanted to say that, and I'm not trying to avoid your questions either. But I just, I don't think it's my place, especially without knowing your medical history. So does anybody have any questions about anything or anything in general or anything about the material before we start? Nope. Everyone good? All right. So what I'm feeling mostly is fatigue. So if I seem like I'm hungover, I'm not. I'm just, like I said, feeling a little bit of the vaccine still. So, but okay. So now we're on the next chapter. It's about periodic properties. And this is going at specifically the periodic table. And so if you remember from the quantum mechanical model, you had the principal quantum number N, angular momentum L, magnetic M sub L, and spin M sub S. So here are the L's. So when L is 0, that's an S orbital. When L is 1, it's a P. L is 2 is D. L is 3 is an F. And so let's start out with the N equals 1, L equals 0. That is the 1s orbital. And when we have one electron in the 1s orbital, we indicate it like so. 1s is the orbital, and this exponent 1 indicates there's one electron in the s orbital. And we then signify it this way. So hydrogen has one electron, at least the atom in the ground state. Well, obviously, electron in the ground state. So the electron is going to be in the 1s orbital, and I just put it spin up. We just like to think positive in the sciences, so that's why we have a +1/2. So hydrogen in its ground state is this. You have one electron in the 1s orbital. That's the principal quantum number n is 1, L is 0, m sub L is 0, and the spin is plus 1/2. It can be minus 1/2, but like I said, we like to think positive. And then helium, now helium has 2 electrons, and the 2 electrons, it's the lowest energy level, the ground state, is still the n equals 1, a equals 0, m sub L is 0, but you can fit 2 electrons in that orbital, provided they have opposite spins. So where you have one is the spin is plus 1/2, and the other one is spin minus 1/2. So, and I'm using the word ground state. Ground state means lowest energy. And remember, like I said before, like we're talking about the hydrogen spectrum. Like if you had to pick something to do the next 5 hours, what would it do? Besides sitting in chemistry class eating candy, right? So it's, you pick low energy things. You pick napping, you pick sitting on your easy chair watching Netflix or something like that, right? So you're doing things that are low energy. You're not doing jumping jacks, you're not doing sprints. That's very hard to do for 5 hours. So you pick the low energy states. So same thing, electrons are the same thing. They like to keep lower energy low, and so that's what they do. They go to the lowest state. They can get excited. They have excited states, but they tend to go to lower energy states. So then we have the Pauli exclusion principle. I mentioned this before. No 2 fermions can have the same set of quantum numbers in the same atom. So so that's why when you have 2 electrons, you can't have the 2 electrons have the exact same set of quantum numbers. That's why the spins have to be plus 1/2, minus 1/2. And now when the 1s orbital is filled, they can then go up into the 2s or 2p. So for hydrogen atoms and also hydrogen-like atoms, meaning there's only 1 electron. So for hydrogen or hydrogen-like atoms, every single value of n, so for n equals 2, 2s, 2p, for n equals 3, 3s, 3p, 3d, these electrons' energies are all degenerate. They mean they're the same energy. So degenerate means the same. So, but if there's more than 1 electron in the atom, then you get what's known as the Stark effect. Well, these exist all the time, but whenever an electron has an external electronic field, the energy levels change. That's known as a Stark effect. And then magnetic field, B is magnetic field. Then the energy levels change. That's known as a Zeeman effect. So if you can remember Stark effect, that's like Tony Stark. That's the Iron Man character. Yes, that's always, well, I don't know if I'm an innocent nerd, but I studied the Stark effect before Iron Man came out. I never read the comics. So I was like, oh, Tony Stark, oh, just like the Stark effect. So, but Zeeman effect, this is more, it causes energy level splits in atoms. So it's more of a magnetic issue, or the cause is more from magnetic fields. The Stark effect, this affects more for bonding. So, okay, and also aforementioned a few times, Coulomb's law. So Coulomb's law, you don't have to quite know this, but I guess I should have put a vector on the radius. So the electronic field is a constant times the charge of Q1, charge of 1 times the charge of second over the radius between the two. And then the force is the radius squared. If you wonder how the physics behind the electronic fields work. I know this is not a physics class, but that's how the magnitude and direction of forces work and for Coulomb's law. That's also what binds an atom together. So the negative electrons and the positive nucleus, they're bound by an attractive force. And also with shielding, so we start off with hydrogen and helium. So hydrogen has 1 electron, helium has 2 electrons, spin up, spin down. Now we're going to go up to another atom, lithium. So now when we have lithium, there's going to be the 1s and the 2s, so spin up, spin, well, it's 3 electrons for lithium as the next element. And For here, for lithium, lithium has 3 protons in its nucleus, but there's 2 electrons here. I know I'm using the Bohr model. There's 2 electrons there and in that orbital. And then there's another electron out here. So, and I know it's a cloud, not a dot, but these 2 electrons here, they kind of, you can't see that, can you? You see yellow? No, I guess, okay, you can see it better on the screen than you can on my iPad. So these 2, the electron cloud here, this kind of shields the electron on the outside. So it really, this electron out here kind of only feels a +1 charge. So the nucleus here is +3, but it really only feels a +1 charge because the electron's out there. And so because of that, this electron out here actually kind of, so remember, electrons have uncertainty in the position, and then it blows up. This electron cloud gets really big. So much bigger than the electron cloud here in the smaller one, partially because these electrons in the core and the inner part feel the full charge of the nucleus. So they get sucked in. And where the electron on the outside just says, like, I'm just going to let myself hang, right? I'm just going to let it all out, and the electron just kind of blows up. And why does it do that? Well, among other things, the electron repels itself. Electron has a weird relationship with itself, right? So electron can be in many different places at once. It occupies a space. It's negatively charged. It actually repels itself because it's a negative charge, and it doesn't like negative charge. So if you just let an electron go, it's not going to shrink down, because then you have a large concentration negative charge. It blows itself up so that it doesn't have to feel its negative self as much. So good thing to think of as you're eating all this Halloween candy, right? So another phenomenon, and I mentioned this last class, is the concept of penetration. So if you look at here is the 1s, and it goes to a peak and comes back down. And but then if you look at a 2p and 2s, the 2s has, remember, there's a node here and has an area called, we refer to as penetration. It penetrates through that electron cloud. The s orbitals tend to feel more of the positive charge, so of the nucleus. So that changes the energy levels a little bit. And you can see here for the 3s, 3p, and 3d. I think you can see the color. Here's the s. The s has 2 humps, and the p has 1 hump. So the s's penetrate better than the p's. So, and then the d's don't have any penetration at all at the 3 level. They would have penetration at the 4 and beyond. So, okay, so then we move on, and we have the German word for this is Aufbau. If you ever see the Aufbau principle, that just means building up in German. And because chemistry used to be was a German thing. You used to, if you were a chemistry major, you had to take German because a lot of the old journals were in German. Now science is predominantly ruled by the United States. So everyone, now if you're in a foreign country and you're gonna be a scientist, you better learn English. So kind of thing. But it used to be German. So, but the building up principle, it works like this. So we start off with hydrogen. Here's hydrogen, spin up, spin down. Actually, I guess you can see that. It's the yellow is brighter on my iPad. It looks better in the screen in blue. So this is hydrogen. Here's helium, 2 electrons. For hydrogen, let me go. Hydrogen, the P's would be the same energy. I'm sorry, the n equals 2, the n equals 3, these would all be degenerate. So, but when you have 2 electron systems, you have the Zeeman effect, you will get the splitting of the energy levels. And the book talks about it in terms of penetration. They don't really mention the Zeeman effect, but I wanted to tell you, I told you I would tell you the truth. It's basically the Zeeman effect. Yeah.
So between 1s and 2s is the Stark?
It would, you mean the difference between these two energy levels?
Yeah.
No, it wouldn't be the Stark effect. That's just the, because I mean, you wouldn't have a Stark effect in hydrogen, and they're different energy levels. That's just the principal quantum number. That's just the n. It's the n increasing, and then it's just the formation of the different energy levels. That's the basis of quantum mechanics. So it's discrete energy levels. And so the Stark effect would be if you had a 2s orbital and you put an electronic field to it, you could split this orbital into two energies. So if you hear it would split into two energy levels above and below. So that's beyond this course.
Okay.
So that becomes more important in bonding. So whereas the Zeeman effect is when you have the 3s be here and the 4s be here. So, okay, so let's go some more building up principles. So this is 1 electron, 2 electrons, helium. Now we have lithium. So you have to go to the second shell, beryllium, and comes next is boron. Now you have two choices next for carbon. So carbon has 6 electrons. So you can either pair it up like this, or you can put it like this. I guess you have a third option. You could do that. So what happens then on the next electron? So when you have degenerate orbitals like this, these are degenerate, so same energy level, you go with parallel spins, and you go 1 orbital at a time. And this is known as Hund's rule. So sometimes it's been referred to as the bus seat rule. I like the way the book explains it. It's like a swimming lap lane rule. So I like to swim. I didn't swim today because I'm feeling like crud. But not that I haven't mentioned it, But I don't know if you guys like to swim laps, but it's so wonderful when you have your own lane. That's wonderful. Sakamoto, yeah. Yeah, I try to go when no one's there. Actually, Mondays I usually go to Kihei Aquatic Center just because I lift weights in Kihei. But usually though, when you can, this is possible. If you could, if there's only one lane in the pool and and only one person's occupied, you could jump in the lane with the person. That's proper, but the guy's probably, or the person swimming there is going to be like, hey, what are you doing? You got this open lane here. Why don't you scoot your butt over there and swim in that lane? Kind of thing. And electrons are like that. It's even worse with electrons because electrons are negatively charged. It's actually energy favorable to be in a different lane. And also, why do they align? So the magnetic fields just align when, generally speaking, it's easier. This happens quite a bit. It's something called the icing model. When you get low enough temperatures, everything just magnetically aligns. So when you have one field, so if you have a magnetic field, it's easier when you jump in something just to align yourself with the field, right? You probably know this too. If you're going somewhere and you see people walking in one direction, you're like, hey, I'm going to walk the way that those guys are walking. When you're in America, you walk on the right side of the road. When you go to New Zealand, you walk on the left side of the road. That's because those people that they do, So same thing with driving, right? So you just kind of go with the flow. Electrons are the same way, but of course, since this one has its spin, it means that the magnetic field is generally pointing in one direction. So the other electrons, when they jump on, they too say, you know what, I'm going to go with you and I'm going to align my field with you. So can you have an electron that says, hey, you know what, I'm going to go ahead and go against you because I'm that kind of an electron? This can happen. This is totally fine. This is an excited state, meaning it's higher energy. So this can happen, and it's going to be higher energy. Same thing with this. This can also happen. There's no rules against that in terms of quantum mechanics. That can also happen, but it's going to be higher energy. So lowest energy is to align one at a time. So we're at 6 electrons for carbon. And now we're going to go, so just building up, alpha building up. Now we're going to 7 for nitrogen. So now we filled the p orbitals, so with 7 electrons. Now we're going to go for oxygen 8. Now we pair them up. Fluorine 9, neon 10. And then likewise going on. So then here's sodium, here's magnesium. Let's see here, it'd be aluminum, phosphorus, sulfur. No, aluminum, silicon, phosphorus, sulfur, chlorine, argon. So sorry, silicon, I missed you. And so on. And these are the ground states, meaning lowest energy. So another interesting point you see, and y-axis here is the energy. The 4s is actually lower energy than the 3d. So when you get to potassium adds here first, then calcium, then I don't know I think it's scantium.
Yes, you're right. You can see it, I'm sure.
Oh. Oh, I forgot about this scantium. Okay. Oh, next is titanium. So then you're in the D shell, and you start adding electrons with parallel spins that way. Okay, so and
Why is copper different?
oh, it's an exception. We'll get to that.
Okay.
So these are the general rules. And a couple other points though. So this one would be, let's see here. So manganese, right? 1, 2, 3, 4. Yeah. Okay, so this is manganese, ground state. And so when you lose electrons, you lose, actually, it's not lose from the highest N. So actually for magnesium plus, it's not going to be this. It's going to be this, where you take an electron from the 4s, even though it's higher energy. It's you lose electrons from the highest principal quantum number. So, but we'll talk about that later. But I wanted to talk about that now, when we had this showing up like this, and you probably wouldn't have manganese plus 1, because this is kind of weird having all these unpaired electrons. It would more likely, you could have it for a brief point in time. For magnesium plus 2, you would be like that. So you lose from the highest N. Okay, so how are we doing? Anybody have any questions? So, and here's another picture of that, and as I mentioned before, here's lithium. And if you can see this, we have the electronic configuration. So hydrogen is going to be 1s first. Helium is going to be 1s squared. And then going on to lithium, you have 1s squared, 2s1, beryllium, 1s squared, 2s2, boron, 1s squared, 2s squared, 2p1, because that's just these exponents, they just tell you how many electrons you have in those orbitals. And you, the reader, have to interpret that. And then also Hund's rule. So for carbon, with 6 electrons, 1s squared, 2s squared, 2p squared, however you want to say it, you understand that it follows Hund's rule and aligns with parallel spins. So, and then for nitrogen, it's parallel spins, and oxygen starts to pair up. And something I think you can, and I already mentioned all these going on. something you might notice that all of these in the n equals 2 level, they all have in common 1s squared. So this is known as the core. So the inside electrons, and then when you have the 2s squared, 2p3, whatever it is, these are known as the valence. So core is, these are the inside electrons, and valence are the outside electrons. And now that chemistry is very superficial. What really defines the chemistry of things are the outside electrons, mostly because they have to do with bonding. I mean, when elements get together, they may or may not bond, and how they're going to bond usually involves the valence, the outside electrons. And so that involves most of their chemical and physical properties can be described by the valence electrons. And so, okay, think of it this way. Another way you can think of it is imagine like bathing suits, right? So something like, it's probably easiest with describing like classically speaking women's swimwear, like a bikini is kind of like your core. So if you're hydrogen or helium, so hydrogen is like wearing a one-piece swimsuit and you're only wearing one item of clothing, and then a helium is like wearing a bikini. You have two pieces of clothing. And then lithium would be like someone wearing a swimsuit, but then putting on a trench coat. The trench coat covers up the other clothing, right? So, I mean, and we see this also with our clothing as well. I mean, you can't, hopefully you can't see what kind of clothes I have on underneath my clothes, right? Because they're covered up, or at least we try to make it invisible. And the same thing with electrons. So the outside electrons kind of cover up the inside ones. And so someone looking at me right now, probably can't see what kind of socks I'm wearing. Hopefully, if my trousers are long enough, kind of thing. So because they're covered by my shoes is the whole idea. So when atoms approach other atoms, they really only feel the outside valence electrons. That's going to come important when it talks about bonding. So let's see if you can remember this, if you're paying attention. What is the ground electronic configuration for sodium? And this has 11 electrons. Some may think it's A. I may think it's B. I think it's, okay, everyone's kind of going for B. B is the right answer. So, and so A is the wrong answer because 2p can only hold 6 electrons. There's 3 orbitals for the L equals 1, M sub L equals -1, 0, or 1. So we have 3 orbitals. So you can only fit 6 electrons in there. A 7th electron would break the Pauli exclusion principle. And I mentioned this in previous classes. Pauli exclusion principle is also the reason why matter has structure. So I can't just mysteriously pass my hand through this water bottle because as my hand is approaching it, the electrons in my hand are trying to occupy the same set of quantum numbers of the electrons in the other object. And then what do? They push back. They push back against each other. And then you have what's known as the normal force in physics, or electron degeneracy in astronomy, or they're not as cool as chemistry, of course, because we have the Pauli exclusion principle. Of course, that's in physics too, but right, that's the origin of that. So you cannot put another electron, you cannot put 7 electrons in the p orbitals. So B is correct. C, same idea. You can't have the 3s and then just go ahead and cram 11 electrons with that quantum number there. You can do it for energy. If this is a photon and you had 11 photons and you want energy level, you can put as many photons on energy levels you want. Doesn't matter because they're bosons. So fermions though, fermions got to have structure. So where photons themselves might have structure, but a group of photons together don't have structure. Yeah.
I was going to ask if fermions and bosons have quarks, but I guess they're their own.
Depends on the electron. It depends on the particle. It seems that electrons are fundamental particles. We've not been able to break them apart. Protons and neutrons are fermions. They are made of quarks. You can get bosons, so certain nuclei, the spins add. So deuterium, which is one proton, one neutron, the magnetic fields actually add together and they form the two spins in one half form a spin of one. So a deuterium nucleus is a boson. So you can actually, if you get them cold enough, you can stack them on top of each other with the same set of, well, the 6 quarks that would make up the deuterium nucleus could then occupy the same energy level state. So you could put as many of those together as you wanted. And one set of quantum numbers. Yeah. Yeah. I mean, which means that the nuclei can stack up on top of each other. The electrons wouldn't though. So you'd have to ionize it. And that would be a weird thing to do though, because you would have a lot of positive charge in that small area as well. But yeah. And so and your answer to your question depends. Some fermions are made of quarks, some are not. So electron is an example. And photons are not made of quarks. So, and they're bosons. And then there's some we don't know, like we hypothesize the existence of something called a graviton, which is where gravity comes from. That has it's theorized or hypothesized to have a spin of 2, and but we've never observed it.
What about when the two black holes crash into each other and make gravitation waves?
As far as what?
Detecting them as their own particle gravity.
We see the waves, we don't see the particles though, because the detector is a bunch of lasers and we see the flexing of space-time. It's moving that. So we really observe it like a wave than we do as a particle. Is that what you're asking?
Yeah.
Yeah, you're
thinking waves could be a hint towards a particle.
That's assuming wave particle duality, but we don't, yeah. Yeah, it's something that's beyond that we have an understanding for. And this discussion is beyond the scope of this class though, by the way. So the rest of you students don't. And I think it's fun to talk about this stuff, but it's just, I don't want you to like, oh crap, time for some particle physics. Space-time. Yeah, so you read a lot of that stuff, cool. You hear things, oh.
Yeah, did you hear that?
All right. If there's other questions, and I wanted to say this one down here. So this one right here, option D. This is actually a possible state, but you notice that there's only one electron in the 2s orbital. This is possible, but this is an excited state. This is an excited electronic state. And we're looking for the ground. Ground means low energy. So low, that's not E. Low is or lowest energy. The lowest energy state of sodium is option B. It's this one here. The option D would be an excited state. That could happen, yeah. Light, heat, chemical reaction, electronic discharge. So just depends. Or it could excite up and it could relax down to a different excited state that's not the ground state. That's another option. Lots of things. The opportunities are endless in this classroom, in the world of chemistry. Okay, and I mentioned before, any other questions? And I guess I didn't check. I probably been yelled at. You guys are okay hearing me Zoom and seeing everything? Usually you pipe up before. Oh, did I even turn on the sound? Oh, I do have the sound on. Good. So I'm assuming by your lack of complaints that you understand me. Okay. All right. So aforementioned, valence means outer electrons, core means inner electrons. And this is Lewis, the Lewis structures. And if you ever see like, well, you have you guys seen this before out of curiosity? You can just have you seen these dot structures before? So a lot of people are shaking their heads yes. This is Lewis that came up with the idea, and he thought that atoms were like boxes, and he thought that the 8 corners of a box were like the way that the number 8 came from for the electrons and bonding, and that is completely wrong. This is the number 8 is mostly right, but this has to do from the s and the p orbitals. S has 2 electrons, p has 6 electrons, and 2 plus 6 is 8. So 8 is an important number when it comes to bonding, because that's known as the octet rule, which we'll talk about soon.
I was gonna say,
Yeah, to octaves, yes. But and for much of chemistry bonding, but he was right about the number 8, wrong about the reason. It's kind of like you ever like do your homework and your teacher marks it wrong, saying, they're like, I got the right answer, like, but you got the wrong way. But I got the right answer. You're like, you're fighting back and forth. That's Lewis. He totally got the right answer for the wrong reason. So
like 4.
I guess, well, I mean, it's a model. I mean, right? I mean, the Greeks are wrong too, and we're probably wrong with quantum mechanics, you know, but we're doing our best. So I guess Lewis is a model. Well, we call it Lewis theory though. So anyway, so here's hydrogen, and I know electrons are really a fuzzy cloud. So electrons are really some sort of fuzzy cloud, but we're gonna get rid of the cloud and just call it a dot. So here's hydrogen, just has 1 dot, and helium has 2 dots. And then lithium, we go back and it has 1 outer electron. Beryllium has 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, neon 8. And so for hydrogen and helium, they only have valence electrons. They have no core electrons. So so this is n equals 1, n equals 2. All of the n equals 2, these have 2 core. So 2 core electrons. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, these all have 2 cores of electrons, two electrons on the inside. And then the n equals 3, quantum number, quantum shell, principal quantum number. These all have 10 cores. So sodium has 11 electrons. It has 1 valence and then 10 core. Magnesium has 2 valence, 2 outside, 10 core. So, and I try to think of it as like clothing. So this is like lithium is like wearing a bikini, but then has a nice trench coat covering up everything. And then beryllium is like, you have a trench coat and then you have a hat. You know, and boron has got 1 gloves, carbon has 2 gloves, kind of thing. You're starting to cover it more and more. And then sodium is just like, oh, got another big trench coat that covers everything else, even the gloves. Yeah.
Are we going to talk about why there's like for helium it has 2 electrons on the side and the beryllium's got 1 and 2?
Not really. It doesn't really. I mean, these tend to bond just for like helium tends to bond up to 2, or hydrogen helium tend to bond up to 2, but we don't. That's not necessarily part of the theory.
Okay.
It's just more that, I mean, you can write it this way, but usually you kind of imply that you pair it up,
Gotcha.
but it's just so it doesn't bond. But helium can bond. So that's a wrong, and the theory's wrong anyways. So,
Not a box.
yep, not a box. And you notice I'm writing n equals 1 equals 2 n equals 3. The rows, the row equals a period. And this is the periodic table. So you arrange them in rows, and it's a periodic table, and the columns, these are known as groups or families. Usually groups are more commonly used than families, but you can hear it be called families as well. So here is then the periodic table with electronic structure. So, and it's a little different than up here with the Lewis model with the dots. But you have then the periodic table with the structures, and we've already talked about this, at least up to neon. And I guess I did it in the chart. I brought it up to argon as well. You can see you just add the electrons incrementally going on up. So any questions? Especially now that Andre's gone. He asked a lot of questions. No. Okay. All right. So let's write the electronic configuration for germanium. I should have erased this. So identify the valence electrons and core electrons. So for germanium, and so let me bring up periodic table. So here's germanium. So you can see right here, it's element number 32. And this here, this is the 1s1, 1s2. These are 2s2, 2p2, 3s2, 3p6. Did I say 2p2? 2p6. This is going to be then 4s, so 1s, 2s, 3s, 4s2. This is 3d, 3d10, 4s2. So here, this is 4s1, 4s2. So when you write this out, it's going to be 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, 3d10, 4p2. So it's got 2 electrons in the 4p orbital. So the valence is going to be here. So germanium has 4 valence electrons because the valence is the highest and only highest principal quantum number. And also this is known as the core. So and a shortcut you can use for this is you can write as a noble gas. So you can put argons. This is argon's configuration. And then write 4s squared, 3d10, 4p2. This is another equally valid way to write this. So you can only put in brackets a noble gas. And why is that? Because, well, that's our convention, first of all. The other thing, why do we do it? Because noble gases are just low energy in general. So does this make sense? Questions with this? So you build up, and I'm trying to show you how the periodic table you can use to describe using the like the building up principle, looking at the different orbitals, and that's the way we organize it, is generally speaking by electronic structure. But then you also have a shortcut, and also the valence of the highest end, valence of the outside electrons. So questions?
So as long as you can place it with a noble gas, you can call it core.
The 3D would be a core as well. The valence is just the highest end.
Also, as long as it's, so core is just anything that's not a valence electron.
Yes. Yeah, question.
Did you say that 3D is higher energy for us?
Yeah, it is.
And then, so it's not ripped out first because for us is easier, or
The electrons are closer to they're the core on the inside. They're physically closer. So the outside ones are the ones that just leave first. It's more of an idea of where they are. And in fact, if you rip a 3D electron out, not a 4s one, the 4s will go down to the 3D one and it'll emit an X-ray.
It's the only, if you take out electron, it's easier to remove 4s than the negative. Is that what you said?
Well, yes. And the electrons are removed from the highest level principal quantum number, highest n first.
Oh, okay.
Yeah, even if
like 3D is a higher level.
even if 3D is higher energy. And if you remove a 3D with like an X-ray, then electrons will go down and it'll like the 4s will go to the 3D.
so it's like for us using.
Yeah. Yep. Other questions? Okay. And here's another explanation of that. I guess I should have gone that with the germanium here. And these, and this chart shows all the electronic structures. And if you've already mentioned, there are some exceptions. So if you look in the D block, the transition metals in the D block, you can see there are a couple exceptions. So copper is an exception. You would expect copper, by the rules I just told you, you'd expect it to be 4s squared 3d 9. But you can see that copper actually goes to 4s 1 3d 10. And the reason for this is because the 4s 1 3d 10 is just lower energy. And there's a certain strength involved when you have a full shell. And you can see this, oh, you also see it with chromium, right? So chromium promotes itself up as well. So you can see there are certain examples. So same thing with molybdenum, but then tungsten doesn't promote. So tungsten doesn't follow the rule. Same thing with seaborgium, it doesn't follow the rule. So, what good is a chemistry class unless, we mention a rule, and then we mention exceptions to the rules, and then we mention exceptions to the exceptions of the rules, right? So why not make chemistry more interesting for you darling students?
The reason why is it out of the scope of the class?
I mean, the reason why is because it's lower energy. And if you did the quantum mechanics, if you did the H psi equals E psi, which is beyond the scope of the class, and you do the Hamiltonian operator and the wave functions, and then it spits out the energy level eigenvalues, you would find actually that for chromium, this is lower energy than the 4s squared 3d4. And then if you did it for tungsten, you would find the opposite true. So, but not 4, it'd be 5s and 6s and 5d respectively. But yes, it's beyond the scope of the class. But I mean, the duh answer is it's lower energy, and we observe it in chemistry.
Does that have anything to do with electrical conductivity?
No, because silver is the most conductive element. We right now we don't have a good theory that starts with quantum mechanics and can build up to macro properties like conductivity. So that's a flaw with our physics right now. So okay, so there are exceptions. And I want you to know that there are exceptions, but you don't really have to know the reason why they exist for this class, because we talk a lot about, well, there'll be some exceptions when we talk about periodic law, but for the most part, electronic configuration, you don't have to worry too much about it, just the fact that they exist. And you can also see this in the Fs. You'll see the, like this one here, right? So gadolinium, you haven't even one goes down to the D. So what the heck? So there's all sorts of interesting things that happen in the chemistry party. So other questions? All right, so you can use the periodic table to describe electronic configurations, which I've already been talking about quite a bit. So for instance, let's use a periodic table to write the electronic configuration for selenium. And selenium is right here in the, so it's going to be, that's in the oxygen family. So you can note that it's right before argon. So if selenium is right here, it's right before argon. So you can write then argon's configuration. Or you can go ahead and do 1s squared, 2s squared, 2p6, 3s squared, 3p6. You can do that, but that's the same thing as argon. But then coming over, so you start here, then come back over to the fourth period, and then you have 4s squared, 3d10, 4p, 1, 2, 3, 4, 4p4, like so. So are you seeing how I'm doing that? Question.
Can you do the same for helium if you want to do lithium? The shortcut?
Lithium, yeah, lithium, you can write it as helium 2s1, or you can write 1s2, 2s1. I mean, a lot of times for the n equals 2 level, it's just easier to just go ahead and write 1s, but it's proper. This is still proper. Because like helium, it's going to be 4 keystrokes versus 3. But I guess you have to do the control plus, to get the superscripts. So that depends on how, how lazy you feel, I suppose. So other questions? Okay. I'm going to try and talk more slowly. So let's see if you can follow. So what is the electron configuration for phosphorus? And phosphorus is right here. I'll do it pink. Here is phosphorus. And this is neon over here. And this is magnesium.
Is that a happy family?
I hope so.
Oh, it's you. Is it? Or no?
Yeah, that's my family. It's been back when I had more hair. Some think it's A. I think it's B. All right, everyone's in this class is going for B. That's the proper answer. So a couple things, right? So it can't be, you're missing 3p5, you're missing the 3 S's, and B is the right answer. C, that looks right, but you tend not to use the elements other than noble gases. Well, you don't. You use the noble gases, and magnesium is not a noble gas. It's an alkaline earth. And this one here, the order is wrong, right? So it's going to be 3s2, 3p3. So you can fit 6 electrons. You can fit 2 electrons in its p's, but you can't fit 3 electrons in the s's. S's have only 1 orbital, whereas the p's have 3 degenerate orbitals. You can fit more. And so, and here also we come to the power of the quantum mechanical model. So the number of valence electrons dictates properties, and then the columns on the periodic table have similar properties, especially chemical properties. And I mentioned they're sometimes called families. So here's a picture of my immediate family. So you can see my parents in the front, and then my 4 siblings with me on the far right. You can see we look like a big blonde tribe, right? So there is no real question of whether or not, like, you know, if one of us, I mean, my brother has 3 biological children and 2 adopted, you know, but like his adopted kids are African American, so it's pretty clear, you know, they're not necessarily from my brother and his wife, which are both white, which is fine. I mean, it's fine to have interracial bondings. My own wife is Asian, for instance. So, but my family, though, my immediate family, there's no adopted in our family. And again, like I said, that's fine to not have. But you can see, you know, we all bear a similar resemblance to each other. And now, and here's my brother in the middle. Here's my father, and here's my nephew. And he's actually he's either 20 or 21. I'm a bad uncle, aren't I? I think he's a sophomore at Notre Dame. So he's a bit younger in this picture, obviously, but you can see that they are holding copper, silver, and gold. And this is copper, silver, and gold are in the same column. They are in the same family. And you might be like, wait a second, copper, silver, and gold, they don't even look alike. Copper's red, silver's silver colored, and gold is yellowish gold colored, right? We can give copper and gold their own names. Like, actually, the truth be told, most metals are silver in color, right? It's hard to tell metals apart. But where copper, silver, and gold are similar, they have similar chemical properties. Where they're noble, they don't react very well. So they have some similar physical properties, but they don't have where they're very much alike is their chemical properties, mainly being unreactive. And I think I mentioned this before. Well, as we know, copper, silver, and gold, they're valuable. So they're expensive. And what makes them expensive is the fact that they're chemical properties, the fact that they're unreactive. So, yeah, question?
Does platinum fall in the same thing?
No, different family.
Is it unreactive?
Yes. Well, as a bulk material, it's unreactive. On the surface, platinum is extremely reactive. So it's a good catalyst. Actually, gold can be too. Believe it or not, gold nanoparticles are very reactive. But as a metal, gold doesn't tarnish. Platinum, like many metals, that oxidize at the surface. Gold, not so much. Silver can oxidize, tends more to react with sulfur. So copper can too, but they're just, in general, copper, silver, gold are not very reactive. So, and platinum is actually more common than gold. So it's not necessarily a rarity, but platinum is just more expensive because it's more useful. So, and just because an element is unreactive doesn't mean it's automatically going to be valuable. And some of the more valuable elements, like so californium and berkelium, are very valuable, and also weapons grade plutonium is extremely valuable. But it's, you know, well, plutonium is pretty reactive. Plutonium is just a reactive metal. But weapons grade plutonium obviously is for making nuclear weapons. It's one of its few uses. And the other ones, like berkelium and californium, they're just hard to make. So they're expensive just from that regards. But I think I use this example, right? So when it comes to metals, of course, we have a Western tradition. If you have something around your finger, maybe I should have worn some rings today. If you have something around your finger, it's a remembrance of a promise. And I see some of you guys are wearing rings, and the rings that we tend to give them that are non-reactive, right? So can you imagine if I was proposing to my now wife, I'm like, as a symbol of my love and devotion, I give you this iron ring to show you if you don't take care of it, it will become flaky and brittle and fall apart, just like my love for you. I mean, that would not be cool, right? We say, no, I give you this gold ring, this platinum ring, because it does not tarnish. Yes, like my love. Right. So, and I mean, but that's our Western tradition.
Yeah, so in the hiring, like if this evaporates and deteriorates, the relationship's over. This is all it's gonna be.
I would throw that sucker into nitric acid saying, ha ha.
I don't know what that is.
Well, it actually would pacify. Like now it's pacified. I don't know. Well, it would dissolve. But anyways, actually for iron rings, I kind of use an example. Have you guys ever heard of the Order of the Engineer? It's a big thing in Canada, and it's trickling down the United States. I know this because I'm in the Order of Engineers. There is a bridge in Canada that broke and fell down from faulty engineering. And so they took the I-beams, which are iron, well, it's carbon steel, which is 98% iron, 2% carbon, and they melted it down, turned it into rings. And what they did was when you had engineers, they would take the rings and you promised that you would be an ethical engineer. And if you did that, you got an Order of an Engineer ring. Now there's enough engineers that from that promise that they no longer have enough. They've used up all the iron. So now I have one. I guess I can bring it to next class or something like that. It's stainless steel. You can get stainless steel. You can get iron as well. I chose stainless steel.
It doesn't oxidize as well.
Not as easily. So there's different types of stainless steel, and you put more stainless steel. There's something called a grain boundary. You can see it on zinc. If you look at zinc, you'll have structure, and if you put different atoms at the grain boundary, it tends to resist corrosion. So, and the different numbers, there's like 316 stainless steel, 304. There's no reason for the numbers. They just mean different things, and you have to look it up in a chart. I don't know what it is, but it's an alloy of different concentrations. But yeah, I have the iron ring, and I mean, other rings, I guess titanium is a common ring now, and also tungsten carbide, which I don't understand why you would choose a ring to be made of tungsten carbide. What? Not really, not compared to platinum. So I'll bring my platinum ring. It's pretty heavy. So platinum's really heavy. I think so. Yeah, it is. Yeah, because it's densest around ruthenium and iridium, and then when you go to the right, so platinum is going to be a little more dense than gold. Yes. So, but how are we doing so far? So families, okay. So, yeah, please.
Just like the general order also affects the pattern too.
Can you say it one more time,
Like,
please?
like the gems and different type, like a diamond or maybe like a ornament one. Would it like also affect like the tone shape of the band itself?
Oh, that. No, the gemstone shouldn't. The tarnish of the band is going to involve the environment and also what metals is connected to. So like you can get like my brother, his wedding ring he's got like a gold outside band with platinum on the inside. And actually that creates a galvanic cell, which actually the gold will corrode to protect the platinum. And so it'd be better off if he had either a pure gold ring or a pure platinum ring. But I talked to him about this and he said, how long is it going to take? I was like, several hundred years. He's like, that's fine. So a lot of these things, they're thermodynamically unstable, but the rate doesn't matter. I have another ring. I guess I should bring in more. I'm gonna do show and tell next class. I have a meteorite ring. You ever heard of those? Yeah. So solubility of metals. And again, this is outside the class. This is just kind of more personal interest stuff right now. Metals can be soluble to a certain extent into each other. And a couple of meteorites, you can have metallic meteorites, which tend to be nickel iron. And you get two phases. You have mostly nickel, a little bit of iron, and mostly iron with a little bit of nickel. And you can see the different colored bands. It's really cool looking. And you could buy them either as platinum bands with a meteorite in the inside, or you can buy titanium. And I picked titanium, even though I am a cheapskate, but it's better because titanium is more reactive than nickel and iron. And then the titanium band will protect the meteorite. If you have tungsten, if you have, actually it would work for tungsten too, but if you had a platinum band with meteorites on it, it'll make the nickel and iron, especially the iron, corrode faster than it would just on its own. So you'll sacrifice the meteorite to save the platinum, and the meteorite costs more than the platinum, right? So it's kind of silly. But
Is it flaky? The meteorite?
no, it's actually pretty. Have you ever seen those in museums, the meteorites?
Well, I'm thinking of lava. Sorry,
Let me see if I have that in the elements. They have it'll be nickel and iron. Do we have the meteorites? Nope.
What does it mean? Like if you see a shooting star and it's like a green tail, which is like
The short answer is I don't know. I could guess a few things. Copper tends to glow kind of green.
Okay.
The other thing that can kind of glow green is oxygen +2. So that's kind of where you get the green color from the northern lights. So it could be O2 plus, I'm sorry, O2 plus. If you have a chemical reaction such that you rip off some electrons from oxygen, you can get colors from that too. So I could hypothesize one of those two things.
Cool.
Jenny would know more than I would though.
Okay.
And the red color, oh, here we go. Here's the meteorite. And if you can see there, you can kind of see the lines in that and it's two phases. So I can show you this in actual real life there, the iron meteorite. So, and some of you are asking, so here's gold here. This is the density. Density is 19.3 and platinum is density is 21. So yes, I was right. It's a little more dense than gold. Does anybody want to look at an element? Oh, I guess I should probably go back to class. But this is still allowed. It's chemistry. Okay. And so families. So here are some families, and aforementioned, we have the alkalis. Alkalis, so lithium, sodium, potassium, rubidium, cesium. The far left, alkaline earths is, and I don't know why we include beryllium. Beryllium is clearly an alkaline earth. It's just toxic. Probably don't want people to touch beryllium. But then again, rubidium and cesium are very reactive. So, but beryllium is toxic as a salt. And the oxygen family, well, I guess the halogen family, and noble gases. So noble, of course, meaning unreactive. And but from I guess in terms of the quantum mechanical model, The alkalis are similar because they all lose one electron. Alkaline earths are similar because they all lose two electrons. And then nitrogen family tends to gain 3. Oxygen family tends to gain 2. Halogens tend to gain 1. And of course, noble gases tend to do absolutely nothing, which is not entirely true. You can get some of them to react. And we'll talk about that in a couple chapters from now. Right. So what is a chemistry class unless I tell you something and then I contradict myself later? So does that bug you guys as students as you're learning this? I always thought it was cool. You know, this is chemistry is like life. Yes. It's not fair. Just like the way I grade you guys, right? No. No. All right, and periodic trends. And you know what? This is probably best if I start talking about this next class, because if I start here, I'll have to stop in 4 minutes and then start again. So, yes.
The reason why you didn't learn this in the beginning, like chapter, like this couldn't be chapter 1.
There is a technique called atoms first in chemistry, and that is one way you can teach it. I like to go through and talk about the boring stoichiometry stuff first. That's the classical way of teaching chemistry. So also atoms first, you go over quantum mechanical. You start with the quantum mechanical model, then go over the periodic trends, and then you go back and then do the same thing. I like doing it the classical way for a few reasons. First of all, if students really don't get the stoichiometry and stuff, like that's important to address that right then and there, and you can do it before like a drop add period. So that's one of the reasons why I do it that way. And most textbooks do the classical one, and I found that students like it better when you follow some sort of pattern, a predictable pattern when you teach. So I try to be as predictable as possible. But I mean, I totally would love to teach chemistry that way, but I would be voted off the island. Can you imagine if I started talking like everything is connected to everything, and this is bonding, this is physical properties, this is equilibrium we haven't talked about yet. There's lots of math. Here's all this math. And like, who is this dude? I mean, it's like what we're trying to do, and it's an observational science. We're trying to break it up into little pieces and all right, you get that, you're good. Like, oh, that was wrong. Here's the new stuff. And then, we try and break it up and so you understand, and then try and also, and I try to bring it like, because I've got the, like to think everything relates to everything, trying to relate it back as much as I can. So it's also a reflection of how we learn as humans. So, but yeah, that's a perfectly valid way. It's called atoms first, but I prefer the not atoms first method. The who's that guy? Linus Pauling, crazy guy, brilliant scientist. Thought he could live forever by taking lots of vitamin C, and some people still think that way.
There was a guy, I'm sure you heard about it, he drinks silver.
Yep, looks like Papa Smurf.
And blue.
Yep. Yeah, that guy's nuts.
There's a couple of them. There was a guy running for Congress or something.
Yeah. All right, so I got 1 minute left in class. Does anybody have any questions other than Papa Smurf? Or I know that guy you're talking about.
Yeah.
All right, then I'm gonna stop recording.